Neutron stars are among the densest stable objects in the observable universe. Tonight, we'll explore what happens when the core of a massive star collapses into a sphere roughly 20 kilometers across, creating matter so compressed that a single teaspoon weighs billions of tons. We'll examine how gravity shapes these objects, why they spin so rapidly, and what role they play in creating the heavy elements we find throughout the cosmos. This is Sleepy Time Universe, where we take our time exploring science and space at a pace designed for rest and reflection. Tonight, we'll move through the physics of neutron stars without rushing, allowing each concept to settle before moving forward. We'll look at magnetic fields that reshape the vacuum of space itself, collisions that forge gold and platinum, and why these objects help us test the limits of our physical theories. Get comfortable. Let your breathing slow. There's no hurry as we explore some of the most extreme physics in nature. Stars exist in a balance between two fundamental forces. Gravity pulls inward, trying to compress all the stellar material toward the center. Nuclear fusion in the core pushes outward, generating enough pressure to resist that gravitational pull. This balance can persist for millions or billions of years, depending on the star's mass. For stars with at least 8 times the mass of our Sun, this equilibrium eventually breaks down. These massive stars burn through their nuclear fuel much faster than smaller ones. While our Sun will fuse hydrogen for about 10 billion years, a star 20 times more massive might exhaust its fuel in just 10 million years. As fusion proceeds, the star creates progressively heavier elements in its core. Hydrogen fuses into helium, then helium fuses into carbon and oxygen, which eventually produce neon, magnesium, silicon, and finally iron. Each stage releases less energy than the one before. Each stage requires higher temperatures and densities. Iron represents a turning point. Fusing iron does not release energy. It consumes energy. When the core becomes primarily iron, nuclear fusion can no longer generate the outward pressure needed to balance gravity. The support mechanism fails almost instantly. The core collapses in less than 1 second. Material that occupied a volume roughly the size of Earth compresses into a sphere perhaps 20 kilometers in diameter. The density becomes so extreme that atoms themselves are crushed beyond recognition. During this collapse, electrons and protons are forced together with such intensity that they combine to form neutrons. This happens through the weak nuclear force, which normally operates only at subatomic scales. The collapsing matter releases neutrinos in enormous quantities as electrons and protons merge. The resulting object consists almost entirely of neutrons packed together so tightly that the entire stellar core becomes, in effect, a single atomic nucleus. This is a neutron star. The outer layers of the original star continue falling inward after the core has already collapsed. When they strike the newly formed neutron star, they rebound violently. This rebound creates the supernova explosion we observe from Earth. The blast releases more energy in a few seconds than our Sun will produce over its entire lifetime. For weeks, this single exploding star can outshine all the other stars in its host galaxy combined. At the center of this cosmic violence sits the neutron star, small, incredibly dense, and spinning rapidly due to conservation of angular momentum from the original star's rotation. The density of a neutron star challenges our everyday understanding of matter. We can state the numbers, but the reality is difficult to grasp through direct comparison. A typical neutron star contains between 1.4 and about 2 solar masses. All of that matter exists within a sphere roughly 20 kilometers in radius. Some neutron stars are slightly larger, Some are slightly smaller, but the general scale remains consistent across observations. Consider a sugar cube filled with neutron star material. That small volume would weigh approximately 100 million tons here on Earth. A teaspoon would weigh roughly 6 billion tons. These figures represent compression far beyond anything we encounter in everyday experience. The density reaches values around 400 trillion times the density of water. To achieve this, the normal structure of atoms must break down completely. The empty space that normally exists between atomic nuclei disappears. The nuclei themselves are pushed together until they touch. This creates matter in a state that doesn't exist anywhere else in the present-day universe, except perhaps in the cores of other neutron stars and in the centers of black holes hidden beyond event horizons. The gravitational field at a neutron star's surface is approximately 200 billion times stronger than Earth's gravity. An object that weighs 1 kilogram on Earth would weigh 200 billion kilograms on a neutron star's surface. This extreme gravity would flatten anything into a layer just atoms thick within microseconds. The escape velocity approaches 1/3 the speed of light. Even light struggles to escape, losing energy as photons climb out of the gravitational well. Time itself runs slower near a neutron star's surface compared to regions of weaker gravitational field. This is gravitational time dilation, a consequence of general relativity. A clock on the neutron star's surface would tick noticeably slower than an identical clock far from the gravitational field. These are not exotic predictions. They are measurable effects that we can detect through astronomical observations, particularly in binary systems where neutron stars orbit companion stars. We cannot observe a neutron star's interior directly. We must infer its structure from theoretical physics and from how these objects behave in our observations. The picture we have assembled suggests several distinct layers, each with its own properties and physics. The outermost layer is an atmosphere only centimeters thick, but heated to millions of degrees. Below this lies a solid crust composed of atomic nuclei arranged in crystalline lattices. These are not ordinary nuclei. They contain far more neutrons than stable isotopes normally have. As we move deeper, the nuclei grow larger and more exotic. Eventually, we reach depths where individual nuclei can no longer exist as separate entities. Instead, matter organizes into elongated structures that physicists have nicknamed nuclear pasta, due to their resemblance to various pasta shapes. These pasta phases represent matter at densities where normal nuclear physics begins to break down. Neutrons and protons are squeezed so tightly that they begin to overlap and merge in ways that have no analog in terrestrial physics. At the very center, conditions may be so extreme that protons and neutrons dissolve into their constituent quarks. This hypothetical quark matter would represent a fundamentally different state, perhaps resembling conditions that existed throughout the universe during the first microseconds after the Big Bang. The exact structure depends on the equation of state of nuclear matter, which describes how pressure relates to density at these extreme conditions. We still do not fully understand this equation of state. Neutron star observations help constrain our theoretical models. When a massive star collapses to form a neutron star, angular momentum is conserved. The original star might have been rotating once every few weeks. As it collapses from a radius of millions of kilometers down to just 20 kilometers, the rotation rate must increase dramatically to preserve angular momentum. This is similar to how figure skaters spin faster when they pull their arms inward, though the scale and speed involved in stellar collapse make that comparison almost inadequate. Newly formed neutron stars can rotate hundreds of times per second. The fastest known pulsar, designated PSRJ 1748-2446 AD, spins 716 times per second. The equatorial surface of this neutron star moves at approximately 1/4 the speed of light. At such rotation rates, the neutron star becomes noticeably flattened at its poles due to centrifugal forces. It takes on an oblate shape, bulging at the equator. Only matter compressed to nuclear density possesses the structural strength to maintain cohesion under these extreme rotational stresses. In 1967, graduate student Jocelyn Bell Burnell noticed unusual regular radio signals while analyzing data from a radio telescope at Cambridge University. The signals arrived with extraordinary precision, pulsing at intervals of approximately 1.3 seconds. The regularity was so precise that the team briefly considered whether they might be detecting artificial signals from an extraterrestrial civilization. They nicknamed the source LGM-1 for Little Green Men. Within months, however, they discovered additional pulsing sources with different periods, making an artificial origin unlikely. The explanation emerged through theoretical work. These pulsars are rotating neutron stars with strong magnetic fields. The magnetic field channels charge particles along field lines, creating beams of radio emission from the magnetic poles. As the neutron star rotates, these beams sweep across space like lighthouse beams. When Earth lies in the path of one of these beams, we detect a pulse of radio waves once per rotation. The pulse period tells us the neutron star's rotation rate directly. Pulsars maintain remarkably stable rotation rates. The best pulsars rival atomic clocks in their long-term stability. We can measure pulse arrival times with precision better than 1 microsecond, allowing us to track changes in rotation rate over months or years. This precision has multiple applications. Pulsar timing helps us study the interstellar medium by measuring how radio waves are delayed and scattered by free electrons in space. It allows us to detect companions around pulsars through gravitational effects on the pulse timing. It even enables tests of general relativity through observations of binary pulsars. Most pulsars gradually slow down as they age. The magnetic field acts like a brake, transferring rotational energy into electromagnetic radiation and particle acceleration. This spin down is predictable and measurable, providing another way to estimate a pulsar's age. Occasionally, pulsars experience sudden speed-ups called glitches. The rotation rate increases abruptly, then gradually relaxes back toward the previous trend. These glitches likely result from interactions between the neutron star's solid crust and a superfluid interior layer that rotates independently. Astronomers have discovered over 3,000 pulsars in our galaxy. They come in several distinct types based on their properties and evolutionary history. Normal pulsars have periods ranging from milliseconds to several seconds. They gradually slow down over millions of years. Eventually, their magnetic fields weaken and their beams fade, making them undetectable from Earth. Millisecond pulsars spin extremely fast, with periods often less than 10 milliseconds. These objects have been spun up through accretion from a companion star. Material falling onto the neutron star transfers angular momentum, increasing the rotation rate. Millisecond pulsars typically have weaker magnetic fields than younger pulsars. Binary pulsars orbit companion stars. The orbital motion creates additional periodic variations in the pulse arrival times as the pulsar moves toward and away from Earth. These systems provide crucial tests of general relativity and allow precise mass measurements of both objects. Some pulsars emit not just radio waves, but also visible light X-rays and gamma rays. The Crab pulsar, located in the Crab Nebula, is visible across nearly the entire electromagnetic spectrum. It was created in a supernova explosion observed and recorded by Chinese astronomers in the year 1054. The alignment between a pulsar's rotation axis and its magnetic axis determines what we observe from Earth. If Earth lies within the cone swept out by the magnetic pole beams, we detect regular pulses. If we lie outside this cone, the pulsar remains invisible to us despite its emission. This geometric effect means we can only detect a fraction of all neutron stars as pulsars. Many neutron stars exist that we cannot observe because their beams do not point toward Earth during their rotation. The magnetic field geometry can be complex. Some pulsars show evidence for multiple emission beams at different heights above the magnetic poles. Others have offset magnetic poles, creating more complicated pulse profiles with multiple peaks per rotation. Understanding this geometry helps us reconstruct the three-dimensional structure of pulsar magnetospheres and test theories about how particles are accelerated to relativistic energies in these environments. Neutron stars possess magnetic fields far stronger than anything we encounter on Earth. A typical neutron star has a surface magnetic field around 1 trillion times stronger than Earth's magnetic field. Earth's magnetic field measures roughly 50 microtesla at the surface. A typical neutron star's field reaches values around 100 million Tesla. For comparison, the strongest continuous magnetic fields created in laboratories measure about 50 Tesla. These fields form during the stellar collapse that creates the neutron star. As the core compresses, conservation of magnetic flux causes the magnetic field to intensify. The field lines that once extended across thousands of kilometers become compressed into a space just tens of kilometers wide. The result is a magnetic field of extraordinary strength, strong enough to affect matter at the atomic level from distances of hundreds of kilometers, strong enough to accelerate particles to nearly the speed of light, strong enough to shape the very structure of the space around the neutron star. Some neutron stars possess magnetic fields even stronger than the typical values. These objects, called magnetars, have surface magnetic fields reaching approximately 100 million Tesla or more. This is roughly 1,000 times stronger than an ordinary neutron star's field. At these intensities, the magnetic field dominates nearly every aspect of the object's behavior. The field stores enormous amounts of energy, comparable to the gravitational binding energy of the entire neutron star. This stored energy can be released suddenly during magnetic reconnection events, creating some of the most powerful electromagnetic outbursts observed in the universe. Magnetars were first identified in the 1990s when astronomers detected unusual X-ray sources that didn't fit the pattern of ordinary neutron stars. These objects produced sporadic bursts of X-rays and gamma rays, sometimes with energies that temporarily overwhelmed detector systems across the solar system. The name magnetar combines magnetic and star, reflecting the dominant role that magnetic fields play in these objects' behavior and emission properties. Near a neutron star, magnetic field strengths become high enough to fundamentally alter the behavior of atoms. Normally, electrons orbit atomic nuclei in relatively spherical patterns. In a strong magnetic field, these orbitals become distorted, elongating along the direction of the field lines. At magnetar field strengths, the distortion becomes extreme. Hydrogen atoms stretch into needle-like shapes thousands of times longer than they are wide. The familiar chemistry of atoms gives way to exotic physics governed primarily by magnetic forces rather than electromagnetic bonding. At distances within about 600 kilometers of a magnetar, the magnetic field becomes strong enough to affect biological tissue directly. The field would align all the atoms in your body along the field lines, disrupting cellular structure and chemistry. Long before that distance, however, the intense radiation would have caused lethal damage. The magnetic fields also affect light itself. Photons traveling through these strong fields can split into pairs of photons with different polarizations. X-rays can merge or scatter in ways that don't occur in weaker magnetic environments. The vacuum itself acquires optical properties similar to a refractive medium. These effects allow astronomers to study magnetic field strengths and geometries by analyzing the polarization and energy distribution of radiation from neutron stars and magnetars. Magnetic fields in neutron stars are not permanent. They gradually decay over millions of years through several mechanisms. Electrical currents in the neutron star's crust generate and maintain the magnetic field, but these currents slowly dissipate as the crust ages and cools. Young neutron stars often have the strongest magnetic fields. As they age, the field weakens. Eventually, after perhaps 100 million years, the magnetic field may become too weak to power significant electromagnetic emission. The neutron star essentially retires, becoming a dark, cooling sphere detectable only through its gravitational effects. Some neutron stars show evidence of magnetic field reorganization events where the field structure suddenly changes. These may be triggered by starquakes that fracture the crust, allowing magnetic field lines to shift into new configurations. Such events often coincide with sudden increases in X-ray emission. The rate of magnetic field decay provides one way to estimate a neutron star's age, though this method has uncertainties because the initial field strength varies from object to object. A neutron star's internal structure consists of several distinct layers, each with its own composition and physical properties. We cannot observe these layers directly, but we can infer their properties from theoretical calculations and from observations of neutron star behavior. The outermost layer is an atmosphere only centimeters thick. Despite its thinness, this atmosphere reaches temperatures of millions of degrees. It consists primarily of hydrogen and helium, though some neutron stars may have heavier elements in their atmospheres. Below the atmosphere lies a solid crust approximately 1 kilometer thick. This crust consists of atomic nuclei arranged in crystalline lattices, similar to how atoms arrange themselves in solid materials on Earth. However, these nuclei contain far more neutrons than any stable isotope found naturally on Earth. The nuclei in the outer crust are held together by electromagnetic forces, much like ordinary matter. Electrons move between the nuclei, conducting electricity and heat. As we move deeper into the crust, the nuclei become progressively more neutron-rich. At the base of the crust, roughly 1 kilometer below the surface, the density becomes high enough that neutrons begin to drip out of the nuclei. These free neutrons can move through the lattice of nuclei, creating a neutron-rich fluid that coexists with the solid lattice structure. Deeper still, at densities approaching those found in atomic nuclei, matter enters exotic states collectively called nuclear pasta. The name comes from the resemblance these structures have to various pasta shapes when visualized in computer simulations. At certain densities, nuclei deform into rod-like structures called spaghetti phase. At other densities, they flatten into sheets called lasagna phase. There may also be phases resembling tubes or Swiss cheese, depending on the exact density and composition. These pasta phases arise because at high densities, the optimal arrangement of neutrons and protons changes from spherical nuclei to more exotic geometries. The strong nuclear force electromagnetic repulsion between protons, and quantum mechanical effects all influence the preferred structure. Nuclear pasta may be the strongest material in the universe. The nuclear forces binding these structures together could give them shear strengths exceeding any terrestrial material by enormous factors. This strength helps the crust resist the immense stresses created by the neutron star's rapid rotation and strong magnetic field. The thickness of the pasta layer and its exact properties depend on the equation of state of nuclear matter, which remains incompletely understood. Different theoretical models predict different pasta structures and transitions between them. Below the crust and pasta layers lies the core, where matter exists at densities exceeding that of atomic nuclei. The core likely contains primarily neutrons, but other particles may also be present, depending on the density and temperature. Protons probably make up a small fraction of the core material, perhaps a few percent by number. Free electrons neutralize the positive charge of these protons. The exact proportion of protons to neutrons affects many neutron star properties, including how the star cools and how compressible the matter is. At the very center of the most massive neutron stars, densities may reach several times the density of an atomic nucleus. At such extremes, new exotic particles could form. Hyperons, which are particles containing strange quarks, might appear. Pions or kaons, which normally exist only briefly in particle accelerators, might form a stable condensate. Some theoretical models suggest that at the highest densities, quarks might exist freely, rather than being confined within neutrons and protons. This hypothetical quark matter would represent a fundamentally different phase, perhaps resembling the conditions throughout the universe during the first microseconds after the Big Bang. The transition from nuclear matter to quark matter, if it occurs, might be gradual, or it might be a sharp phase boundary. The details affect how compressible the neutron star matter is, which in turn affect the maximum possible mass a neutron star can support before collapsing into a black hole. Much of a neutron star's interior likely exists in superfluid and superconducting states. Superfluids flow without friction or viscosity. Superconductors conduct electricity without resistance. These are quantum mechanical states of matter where particles move in a coordinated way, rather than independently. Neutrons in the inner crust and core probably form a superfluid at temperatures below about 1 billion degrees. This superfluid can rotate independently of the solid crust, creating the differential rotation responsible for pulsar glitches. Protons in the core may form a superconductor, allowing electric currents to flow without dissipation. These currents could help maintain the neutron star's magnetic field over long timescales. The interaction between the superfluid neutrons and superconducting protons affects how the magnetic field evolves and how energy is transported through the core. These quantum states exist at temperatures and densities far from everyday experience. The neutron superfluid exists at temperatures millions of times higher than terrestrial superfluids like liquid helium. Understanding how superfluidity and superconductivity work under these conditions requires extending our theoretical models into new regimes. The equation of state describes how matter responds to pressure at different densities. It's essentially a relationship between pressure, density, temperature, and composition. For neutron stars, the equation of state at high densities remains one of the biggest uncertainties in our understanding. Different theoretical models of nuclear forces predict different equations of state. A stiff equation of state means matter resists compression strongly. A soft equation of state means matter compresses more easily under pressure. The stiffness of the equation of state directly determines the maximum mass a neutron star can support. Stiffer equations allow higher maximum masses. Softer equations result in lower maximum masses. Observations of neutron star masses and radii provide constraints on the equation of state. If we measure a neutron star with a mass of 2 solar masses, we know the equation of state must be stiff enough to support that mass against gravitational collapse. Gravitational wave observations of neutron star mergers provide another way to constrain the equation of state. The tidal deformability, which measures how much the neutron star stretches in response to its companion's gravitational field, depends on the equation of state. Stiffer equations produce less deformation. Softer equations allow more stretching. Combining different observational constraints helps narrow down the possible equations of state. This in turn helps us understand nuclear forces at densities we cannot recreate in laboratory experiments. Many neutron stars exist in binary systems where they orbit another star. The companion might be a normal star, a white dwarf, another neutron star, or even a black hole. These binary systems enable measurements and observations impossible for isolated neutron stars. In some binaries, the neutron star accretes material from its companion. If the companion is a normal star that has expanded beyond its Roche lobe, material flows from the companion onto the neutron star through an accretion disk. As material spirals inward through the accretion disk, it heats up through friction and compression. By the time it reaches the neutron star's surface, it has heated to millions of degrees and emits primarily in X-rays. These X-ray binaries can be among the brightest X-ray sources in the sky. The infalling material carries angular momentum, which it transfers to the neutron star. Over millions of years, this process can spin the neutron star up from a slow rotation rate to millisecond periods. This explains why most millisecond pulsars are found in binary systems. Material accumulating on a neutron star's surface can reach high enough temperatures and densities to undergo nuclear fusion. When a critical amount of material has accumulated, fusion ignites suddenly across the entire surface. This thermonuclear explosion releases enormous energy in a few seconds, creating an X-ray burst that can briefly outshine the neutron star's steady accretion emission by factors of hundreds. The burst heats the surface to temperatures exceeding 1 billion degrees. After the burst, accretion continues, gradually building up a new layer of material until conditions are right for another burst. Some neutron stars produce X-ray bursts every few hours or days with remarkable regularity. These bursts provide a way to study nuclear physics under extreme conditions. The fusion reactions occur at temperatures and densities far beyond anything achievable in terrestrial laboratories. The composition of the accreted material and the neutron star's surface gravity affect the burst properties in measurable ways. Occasionally, accumulated material over larger areas or depths ignites in particularly powerful bursts called superbursts. These rare events release even more energy and last for hours or days, rather than seconds or minutes. Binary systems containing 2 neutron stars provide extraordinary laboratories for testing Einstein's general theory of relativity. The first binary pulsar, P SRB 1913+16, was discovered in 1974 by Russell Hulse and Joseph Taylor. In this system, both neutron stars orbit their common center of mass every 8 hours. As they orbit, the gravitational pull of the companion affects the timing of pulses from the observable pulsar. By analyzing these timing variations precisely, astronomers determined both stars' masses, the orbital period, and many other orbital parameters. General relativity predicts that orbiting masses emit gravitational waves, ripples in spacetime that carry energy away from the system. This energy loss should cause the orbit to shrink gradually, bringing the neutron stars closer together over time. Hulse and Taylor measured the orbital decay rate with extraordinary precision over decades of observations. The measured rate matched Einstein's predictions to better than 1 part in 1,000. This provided the first indirect detection of gravitational waves, earning Hulse and Taylor the Nobel Prize in Physics in 1993. Many binary pulsars have been discovered since 1974. The system PSRJ 0737-3039 contains 2 pulsars, both detectable from Earth. This double pulsar allows even more precise tests of general relativity, because we can observe both neutron stars and how they affect each other. These systems have confirmed general relativity's predictions for orbital decay, changes in orbital orientation, gravitational redshift, and time dilation. Some tests have confirmed Einstein's equations to better than 1 part in 10,000, making general relativity one of the most precisely tested theories in physics. As gravitational wave emission removes energy from a binary neutron star system, the orbit gradually shrinks. This process occurs over hundreds of millions of years for wide binaries, but accelerates as the orbit tightens. In the final seconds before merger, the neutron stars spiral inward at accelerating rates. They orbit each other hundreds of times per second, with orbital velocities approaching 1/3 the speed of light. The gravitational waves produced during this phase carry enormous power, briefly exceeding the electromagnetic output of all stars in the observable universe combined. As the neutron stars approach within a few hundred kilometers, tidal forces become significant. Each neutron star raises tides on its companion, distorting both objects from perfect spheres. The amount of distortion depends on the equation of state. Stiffer matter resists tidal deformation more than softer matter. When the neutron stars finally touch, they don't simply combine into a larger neutron star. The collision is violent, heating material to billions of degrees and ejecting some matter into space at relativistic speeds. The rotation is so rapid and the tidal force is so extreme that the merged object becomes highly distorted. What forms after merger depends on the combined mass. If the total mass exceeds the maximum that neutron star matter can support, the object collapses into a black hole. This might happen immediately or after a brief period where rotation and pressure delay the collapse. If the mass is below this limit, a massive neutron star forms. This remnant gradually settles down over seconds or minutes, radiating away excess energy and angular momentum through gravitational waves and electromagnetic emission. The matter ejected during a neutron star merger undergoes rapid nucleosynthesis. This material is extremely neutron-rich, with neutron-to-proton ratios far exceeding anything found in normal matter. In this environment, atomic nuclei can capture neutrons faster than they decay radioactively. This rapid neutron capture process, called the R process, builds up heavy elements all the way to uranium and beyond within seconds. The newly formed heavy elements are highly radioactive. They decay through various pathways, releasing energy that heats the expanding ejector. This heating causes the material to glow, creating a transient called a kilonova. Kilonova light curves show distinctive features. They rise to peak brightness over about 1 day, then fade over the following weeks. The color changes as different radioactive isotopes decay. Early emission tends toward blue wavelengths. Later emission shifts toward red and infrared as heavier, more slowly decaying elements dominate. The first clearly identified kilonova was observed in August 2017, following gravitational wave detection of a neutron star merger designated GW 170817. Telescopes worldwide observed this event across many wavelengths, providing unprecedented detail about kilonova physics and R-process nucleosynthesis. Analysis of the light curves and spectra confirmed that neutron star mergers produce large quantities of heavy elements, including gold, platinum, and rare earth elements. A single merger can create masses of gold, equivalent to several times Earth's mass. Most elements lighter than iron are created through fusion in stellar cores during a star's normal lifetime. Elements heavier than iron require different processes because fusing them consumes rather than releases energy. One way to create heavy elements is through slow neutron capture, called the S process. This occurs in evolved stars where neutrons are produced at relatively slow rates. Nuclei capture neutrons one at a time, with pauses for radioactive decay between captures. The S process can build elements up to lead and bismuth, but it cannot create the heaviest elements or produce certain neutron-rich isotopes. For these, we need rapid neutron capture, the R process. The R process requires environments with extremely high neutron densities and temperatures. Nuclei must capture neutrons faster than they can undergo radioactive decay. This builds very neutron-rich isotopes that would normally be unstable, but don't have time to decay before capturing more neutrons. Once the neutron supply drops, these neutron-rich nuclei undergo chains of radioactive decay, eventually settling into stable isotopes. The decay paths determine which final elements are produced in what proportions. For decades, astronomers debated where in the universe conditions are right for the R process. Supernovae were long considered the primary site, but detailed models struggled to produce the observed abundances of R process elements. The observation of GW 170817 and its associated kilonova settled this debate. Neutron star mergers clearly produce R process elements in quantities matching what we observe throughout the universe. The heavy elements created in neutron star mergers don't remain concentrated at the collision site. The ejector expands at velocities of tens of thousands of kilometers per second, spreading through interstellar space. Over millions of years, this enriched material mixes with interstellar gas clouds. When new stars form from these clouds, they incorporate the heavy elements. Rocky planets forming around those stars contain these elements as well. Earth's abundance of elements heavier than iron came from ancient neutron star mergers that occurred before our solar system formed. Every atom of gold, platinum, uranium, and other R-process elements on Earth was created in these collisions billions of years ago. The frequency of neutron star mergers determines how quickly galaxies become enriched with heavy elements. Current estimates suggest mergers occur at a rate of roughly 10 to 100 per million years per galaxy, though this varies with galaxy type and cosmic epoch. This rate is sufficient to explain the observed abundances of R-process elements in stars and interstellar gas throughout our galaxy and in other galaxies we can observe. The pattern of element abundances provides a fossil record of past neutron star mergers. Many heavy elements play crucial roles in biological systems and technological civilizations. Iodine, created primarily through the R process, is essential for thyroid function in vertebrates. Molybdenum, another R process element, is a key component in certain enzymes. While these particular elements aren't absolutely required for all possible forms of life, they illustrate how neutron star mergers connect to biological evolution through cosmic element creation and distribution. For technological civilizations, rare earth elements produced in our process nucleosynthesis enable many modern technologies. These elements have unique electronic and magnetic properties that make them essential for everything from computer displays to MRI machines to electric motors. The availability of these elements on Earth results directly from neutron star mergers that enriched the gas cloud from which our solar system formed. Had fewer mergers occurred in our galactic neighborhood's history, Earth might have formed with different elemental abundances, potentially affecting both geological evolution and the development of life and technology. This represents one of the most profound examples of cosmic connectivity. Violent collisions between stellar remnants billions of years ago determined the chemical composition of our planet and enabled the existence of elements we consider essential. Einstein's general theory of relativity predicts that accelerating masses create ripples in spacetime itself. These gravitational waves propagate at the speed of light, carrying energy away from their source. For decades, gravitational waves remained purely theoretical predictions. They were too weak to detect even from the most energetic cosmic events. This changed in September 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from merging black holes. 2 years later, in August 2017, LIGO and its European partner Virgo detected gravitational waves from a neutron star merger. This event, designated GW 170817, opened a new era in astronomy by combining gravitational wave detection with observations across the electromagnetic spectrum. The gravitational wave signal from GW 170817 lasted about 30 seconds as the two neutron stars spiraled together and merged. The signal frequency increased over time as the orbit tightened, by a pattern called a chirp. By analyzing the chirp's details, scientists extracted information about the neutron star's masses, spins, and tidal deformability. This data provided constraints on the equation of state of nuclear matter and the maximum mass neutron stars can support. About 2 seconds after the gravitational wave signal ended, gamma-ray satellites detected a short gamma-ray burst from the same direction. This confirmed theoretical predictions that neutron star mergers produce these high-energy events. Within hours, optical telescopes located the merger site in Galaxy NG C 4993, about 130 million light-years from Earth. They observed a new bright source that hadn't been present in previous images. This was the kilonova powered by radioactive decay of heavy elements created in the merger. Over the following days and weeks, telescopes operating at radio, infrared, optical, ultraviolet, X-ray, and gamma-ray wavelengths monitored the fading kilonova. Each wavelength provided different information about the ejector composition, temperature, and velocity. This coordinated campaign, involving thousands of astronomers and dozens of telescopes worldwide, demonstrated the power of multi-messenger astronomy. Combining gravitational wave observations with electromagnetic data provided far more information than either type of observation could reveal alone. The observations confirmed that neutron star mergers produce our process elements in quantities matching what we observe throughout the universe. They provided new constraints on the equation of state of nuclear matter. They tested general relativity in the strong field regime. They enabled a new measurement of the universe's expansion rate. While mergers produce brief, powerful gravitational wave signals, some neutron stars may produce weaker continuous gravitational waves if they have asymmetric shapes. A perfectly spherical neutron star rotating on its axis, produces no gravitational waves. But if the neutron star has a mountain on its surface, even just a few centimeters tall, the rotating asymmetry creates a continuous gravitational wave signal. These mountains might exist due to magnetic stresses that deform the crust, or from crystalline structure imperfections, or from uneven heat distribution. The signal would be weak but persistent, potentially detectable if we know where to look and can integrate the signal over long periods. Searches for continuous waves target known pulsars, where we already know the rotation frequency and position. By analyzing months or years of gravitational wave detector data, scientists can potentially detect these faint signals despite their weakness. No continuous gravitational wave has been definitively detected yet, but upper limits on possible signal strengths constrain how large neutron star mountains can be. This in turn provides information about the strength of crustal material and magnetic field stresses. When a pulsar glitches, the sudden change in rotation might excite oscillations in the neutron star. These oscillations could produce transient gravitational wave signals lasting seconds to hours. Different oscillation modes involve different types of motion. Some modes involve the entire star pulsing radially. Others involve surface waves or torsional vibrations. Each mode produces gravitational waves with characteristic frequencies related to the neutron star's mass, radius, and internal structure. Detecting gravitational waves from pulsar glitches would provide a new way to probe neutron star interiors. The oscillation frequencies depend on the equation of state, superfluid properties, and magnetic field strength in ways that complement information from electromagnetic observations. The challenge is that glitches are unpredictable, and the expected gravitational wave signals are weak. Current detectors may not be sensitive enough to detect these signals except from the nearest and most violent glitches. Future gravitational wave observatories with improved sensitivity may make glitch detection routine, adding another tool to our observational capabilities for studying neutron stars. Among neutron stars, magnetars represent the most magnetically extreme objects. Their surface magnetic fields reach approximately 100 million Tesla, roughly 1,000 times stronger than typical neutron stars and trillions of times stronger than Earth's field. At these field strengths, magnetic forces dominate nearly all aspects of the magnetar's behavior. The field energy alone is comparable to the gravitational binding energy of the entire neutron star. This stored magnetic energy can be released suddenly in violent outbursts. Magnetars likely form when the collapsing stellar core happens to have a particularly strong magnetic field and rapid rotation. During collapse, the field becomes amplified through compression. The exact combination of rotation rate, initial field strength, and core dynamics required to produce a magnetar rather than a normal neutron star remains an active area of research. Not all magnetars look the same. Some rotate rapidly with periods of a few seconds. Others rotate more slowly with periods of 10 seconds or more. Some show frequent bursting activity. Others remain relatively quiescent for years before erupting. The population of known magnetars is small, with only about 30 confirmed as of the early 2000s. They represent perhaps 10% or less of the neutron star population, making them relatively rare outcomes of stellar death. The immense magnetic stresses inside a magnetar create forces on the solid crust that can exceed the material's breaking strength. When this happens, the crust fractures in events called starquakes. These are not earthquakes in the familiar sense. The crust material is denser and stronger than any terrestrial rock. The energy released in a magnetar starquake can exceed all the earthquakes on Earth over thousands of years combined. When the crust fractures, it suddenly changes shape. The magnetic field lines threading through the crust are anchored to it. As the crust shifts, these field lines are suddenly twisted and stressed. This triggers magnetic reconnection events where field lines break and rejoin in new configurations, releasing enormous bursts of energy. The energy release heats the magnetar's surface to billions of degrees for brief periods. It accelerates particles to nearly the speed of light. It creates intense bursts of X-rays and gamma rays that can be detected from across the galaxy. Some Magnetar outbursts are relatively modest, lasting seconds and releasing energy equivalent to what our Sun produces over several years. Others are more dramatic, with energies exceeding the Sun's total output over centuries. The most powerful Magnetar outbursts are called giant flares. Only a handful have been observed, but they rank among the most energetic electromagnetic events in the universe. The giant flare from SGR 1806-20 in December 2004 released more energy in 1/10 of a second than our Sun will produce in 150,000 years. The burst was so intense that it temporarily saturated detector systems on satellites throughout the solar system. Even though SGR 1806-20 lies about 50,000 light-years from Earth, the gamma-ray flux was strong enough to measurably affect Earth's ionosphere. The burst created increased ionization in the upper atmosphere, causing changes in radio wave propagation measurable by instruments on the ground. If such a flare occurred from a magnetar just 10 light-years away, it would deliver enough radiation to Earth to cause significant damage to the ozone layer, potentially triggering ecological disruption or even mass extinction events. Fortunately, the nearest known magnetar lies safely thousands of light-years distant. The probability of a nearby magnetar producing a giant flare is extremely low, posing no realistic threat to Earth. Giant flares likely occur when especially large regions of the magnetar's crust fracture simultaneously, triggering massive magnetic reconnection, events that restructure significant portions of the magnetosphere. The exact trigger mechanisms and why some magnetars produce giant flares, while others don't remain subjects of ongoing study. Magnetars do not remain magnetically extreme forever. Over millions of years, the powerful magnetic field gradually weakens through several processes. Electric currents in the crust maintain the field, but these currents slowly dissipate due to electrical resistance in the crustal material. Even though the crust may be superconducting in some regions, there are still mechanisms for energy loss. As the field weakens, magnetar activity declines. The X-ray emission fades. Bursts become less frequent and less energetic. Eventually, after perhaps 10 million years, the object may become indistinguishable from an ordinary neutron star. This suggests that many old neutron stars may be extinct magnetars. Their magnetic fields have decayed to the point where they no longer produce the dramatic bursts and high X-ray luminosity characteristic of active magnetars. Some magnetars show periodic behavior with active phases separated by quiescent periods. The object might burst frequently for months or years, then enter a quiet phase lasting decades before becoming active again. This cyclic behavior likely reflects complex interactions between the magnetic field, crust, and internal structure. The relationship between magnetars and other types of neutron stars continues to be refined as observations reveal transitional objects with properties intermediate between magnetars and ordinary pulsars. Most of our detailed knowledge about individual pulsars comes from radio timing observations. Radio telescopes detect the pulses and measure their arrival times with microsecond precision or better. By accumulating months or years of timing data, astronomers can measure the pulsar's rotation period with extraordinary precision. They can detect period changes that reveal the spin-down rate, which in turn indicates how much rotational energy the pulsar is losing. For pulsars in binary systems, the orbital motion creates periodic variations in pulse arrival times. As the pulsar moves toward Earth in its orbit, pulses arrive slightly earlier. As it moves away, they arrive slightly later. These Doppler shifts allow precise determination of orbital parameters. Radio timing also reveals pulsar glitches, changes in dispersion measure caused by variations in interstellar electron density, and even the presence of planets orbiting the pulsar through gravitational effects on the timing. The technique requires stable, sensitive radio telescopes and sophisticated data analysis methods. Large facilities provide some of the most precise pulsar timing data, enabling tests of general relativity and searches for gravitational waves using pulsar timing arrays. Many neutron stars emit X-rays from hotspots on their surfaces or from material accreting from companion stars. X-ray satellites can detect these emissions and study their properties. The Chandra X-ray Observatory provides high spatial resolution, allowing astronomers to pinpoint X-ray sources precisely and separate individual neutron stars from nearby sources. Other X-ray satellites offer high sensitivity for detecting faint sources and studying their spectra in detail. X-ray observations reveal surface temperatures, hotspot locations and sizes, and how emission varies with rotation phase. They can detect Magnetar outbursts and monitor how these events evolve over time. Spectroscopic observations in X-rays measure absorption lines from elements in the neutron star atmosphere. The line shapes and energies depend on the gravitational field and magnetic field strength, providing diagnostics for both properties. Future X-ray missions will offer improved sensitivity and spectral resolution, enabling even more detailed studies of neutron star emission mechanisms and surface conditions. While most neutron stars emit primarily in radio waves or X-rays, some are bright enough to detect in optical and infrared wavelengths. The Crab pulsar was the first neutron star detected optically, flashing with the same period as its radio pulses. Optical observations can measure surface temperatures for the hottest neutron stars. They can also detect emission from surrounding nebulae powered by the neutron star's particle wind and radiation. Infrared observations are particularly useful for detecting faint neutron stars whose thermal emission peaks at longer wavelengths. They can also penetrate dust that might obscure optical light, allowing observations of neutron stars in crowded star-forming regions. Some millisecond pulsars in binary systems have optical counterparts. Observing these companions provides information about the binary evolution and mass transfer history that spun up the pulsar to its current rapid rotation. High-energy gamma-ray observations from space-based telescopes reveal the most energetic emission from neutron stars. The Fermi Gamma-Ray Space Telescope has detected thousands of gamma-ray sources, including hundreds of pulsars. Gamma-ray observations provide information about particle acceleration in pulsar magnetospheres. The high-energy photons come from electrons spiraling in magnetic fields, or from inverse Compton scattering where low-energy photons gain energy from collisions with high-energy particles. Some neutron stars are visible only in gamma rays, emitting little or no detectable radiation at other wavelengths. This might occur if the radio beam doesn't point toward Earth, but the gamma-ray emission pattern is broader and does intersect our line of sight. Magnetar outbursts often include gamma-ray components. Detecting these bursts helps identify and monitor magnetar activity, even when the objects are too distant for detailed X-ray observations. When a neutron star first forms in a supernova explosion, the core temperature can exceed 100 billion degrees. This enormous heat comes from the gravitational potential energy released during collapse and from the energy of the nuclear processes that created the neutron star. The interior doesn't cool instantly. Heat must be transported from the core to the surface before it can radiate away into space. Several mechanisms transport this heat, including conduction through the crust, convection in some regions, and neutrino emission from the core. Neutrinos play a crucial role in neutron star cooling, especially during the first 1,000 years. These nearly massless particles barely interact with ordinary matter, allowing them to escape freely from the dense interior. They carry energy away much faster than photons could, because photons get absorbed and scattered repeatedly before escaping. The neutrino cooling rate depends on what processes can occur in the core. Different particle populations and reactions produce neutrinos at different rates. This makes neutron star cooling sensitive to the composition and physical state of matter at nuclear densities. While the interior temperature decreases rapidly at first, the surface temperature we observe changes more slowly. The surface temperature depends on the heat flux from the interior and on the properties of the insulating crust. A newly formed neutron star might have a surface temperature around 10 million degrees. This gradually declines to around 1 million degrees over the first million years. Ancient neutron stars, billions of years old, may have surface temperatures below 100,000 degrees. At these temperatures, neutron stars emit primarily in X-rays. Observing these faint thermal X-ray emissions from nearby neutron stars allows astronomers to measure surface temperatures and compare them to theoretical cooling models. Different cooling scenarios predict different temperature versus age relationships. Fast cooling occurs if certain exotic particles exist in the core, providing additional neutrino emission pathways. Slow cooling occurs if the core contains only neutrons, protons, and electrons in their simplest configurations. By measuring surface temperatures for neutron stars of various ages and comparing to theoretical predictions, we can constrain the composition of neutron star matter. This provides one of the few ways to test theories about particle physics and nuclear densities. Theoretical cooling curves plot temperature against time for neutron stars with different properties. The curves show steep initial declines as neutrino emission rapidly removes heat from the core, followed by more gradual cooling as photon emission from the surface becomes the dominant energy loss mechanism. The exact curve shape depends on many factors: the neutron star's mass, the presence of superfluidity in the interior, the composition of the core, and the properties of the crust. Magnetic fields can also affect cooling by influencing heat transport in the crust. Some young neutron stars cool faster than standard models predict. This suggests rapid cooling mechanisms are operating, possibly indicating the presence of exotic particles in the core. Other neutron stars cool more slowly, suggesting more conventional compositions. The diversity of observed cooling rates indicates that neutron stars do not all have identical internal structures. Different formation conditions, masses, or compositions lead to measurable differences in thermal evolution. Some processes can reheat neutron stars or slow their cooling. In binary systems, accretion of material onto the neutron star's surface releases gravitational potential energy. This energy heats the surface and underlying layers, raising the observable temperature above what cooling alone would predict. Even in isolated neutron stars, magnetic field decay can deposit energy into the crust over millions of years. As crustal currents dissipate, They generate heat that partially offsets cooling. Friction between the superfluid interior and the solid crust during glitches or steady differential rotation can also generate heat. The exact amount depends on the coupling strength between these components and how much relative motion exists. These heating mechanisms complicate the interpretation of temperature measurements. To accurately determine a neutron star's age and composition from its temperature, we need to account for any reheating that might have occurred. Neutron stars create gravitational fields far stronger than anything accessible through solar system tests of general relativity. At the surface of a neutron star, space-time curvature becomes so extreme that relativistic effects are large rather than small corrections. This strong field regime provides crucial tests of Einstein's theory. If general relativity breaks down or needs modification at strong curvatures, neutron star observations might reveal the deviations. So far, all tests have confirmed general relativity's predictions. The theory accurately describes orbital decay in binary pulsars, gravitational time dilation, light bending, and other effects measured through pulsar timing and gravitational wave observations. When radio pulses from a pulsar pass close to a massive object, they experience a time delay due to the curvature of spacetime. This is called the Shapiro delay, named after physicist Erwin Shapiro, who predicted it. In binary pulsar systems, we can measure this delay when pulses pass near the companion star. The delay varies with orbital phase, reaching maximum when the pulses pass closest to the companion. The magnitude of the delay depends on the companion's mass. By measuring the Shapiro delay precisely, astronomers can determine the companion mass without relying on orbital mechanics alone. This provides an independent mass measurement that helps break degeneracies in the orbital solution. The observed delays match general relativity's predictions to high precision, providing another confirmation of the theory in the strong field regime. In Newtonian gravity, elliptical orbits maintain fixed orientations in space. In general relativity, the orbits of close binary systems precess, with the orientation rotating over time. This periastron advance is measurable in binary pulsars with eccentric orbits. The rate of precession depends on the system's total mass and orbital separation. For tight binary pulsars, the precession can be several degrees per year, easily measurable through timing observations. The observed precession rates match general relativity's predictions precisely, with uncertainties of just a few parts in 1,000. This confirms that general relativity correctly describes orbital dynamics even when gravitational fields are intense, and orbital velocities approach significant fractions of light speed. Light emitted from a neutron star's surface must climb out of the deep gravitational potential. In doing so, it loses energy, becoming redshifted to longer wavelengths. This gravitational redshift depends on the ratio of mass to radius. For typical neutron stars, the redshift is around 20 to 30%. Light emitted at 500 nanometers appears at wavelengths around 600 to 650 nanometers after escaping the gravitational field. Measuring gravitational redshift requires identifying atomic or nuclear lines in neutron star spectra. The observed wavelengths differ from the laboratory rest wavelengths due to both gravitational redshift and any Doppler shifts from the neutron star's motion. Detected gravitational redshifts have been consistent with general relativity, though the measurements are challenging and uncertainties remain larger than for other tests. Rotating masses drag spacetime around with them, an effect called frame dragging, or the lens-Thirring effect. For rapidly rotating neutron stars, this effect becomes measurable. Frame dragging affects orbital planes of material around the neutron star. It causes precession of accretion disks and can create observable signatures in the X-ray emission from accreting systems. Some observations of neutron stars in binary systems show evidence for frame-dragging effects, though alternative explanations sometimes exist. Confirming frame-dragging unambiguously requires precise measurements and detailed modeling. The magnitude of observed effects is consistent with general relativity's predictions for rapidly rotating massive bodies in the strong field regime. Gravitational wave observations provide powerful tests of general relativity in highly dynamical strong field conditions. The binary neutron star merger G W 170817 allowed multiple tests simultaneously. The waves arrived with frequencies and amplitudes matching general relativity's predictions for inspiraling neutron stars. The phase evolution of the waveform followed the expected pattern. The polarization was consistent with general relativity's two allowed polarization states. By comparing the arrival times of gravitational waves and electromagnetic signals from the merger, scientists confirmed that gravitational waves travel at the speed of light to within 1 part in 10 to the 15th power. This ruled out many alternative theories of gravity that predict different wave propagation speeds. These tests operate in regimes where gravitational fields are strong, change rapidly, and involve large masses moving at relativistic speeds. General relativity passed all tests, confirming its validity under conditions far beyond those accessible through solar system experiments. Neutron stars continue cooling for billions of years after their formation. After the first few million years, when neutrino emission has subsided, photon radiation from the surface becomes the primary cooling mechanism. This proceeds much more slowly. By an age of 1 billion years, surface temperatures have dropped to around 100,000 degrees or less. The neutron star emits primarily in far ultraviolet and soft X-ray wavelengths. It's much fainter than younger neutron stars, difficult to detect unless it's nearby, or we have very sensitive instruments. Ancient neutron stars, billions of years old, may have surface temperatures below 10,000 degrees. They emit mostly in ultraviolet, or even visible wavelengths, becoming increasingly difficult to distinguish from faint white dwarfs without detailed spectroscopic observations. The cooling continues essentially forever, limited only by the universe's expansion and the eventual heat death of the cosmos on timescales of 10 to the 100th power years or more. Long before then, neutron stars will have cooled to temperatures approaching the cosmic microwave background radiation. While neutron stars cool, their magnetic fields also evolve. The electrical currents maintaining the field gradually dissipate due to various resistive processes in the crust and core. For typical neutron stars, the magnetic field decays on timescales of hundreds of millions of years. Young pulsars have fields around 1 trillion times Earth's field. After a few 100 million years, the field has weakened by factors of 10 or more. This decay explains why millisecond pulsars, which are old neutron stars spun up by accretion, typically have weak magnetic fields. The fields had billions of years to decay before the accretion process began. For magnetars, the decay may proceed differently due to the initially much stronger field. The decay might be faster because stronger currents generate more resistive heating. Or it might be slower if the field configuration is particularly stable. Eventually, all neutron star magnetic fields likely decay to negligible strengths. Ancient neutron stars might have fields no stronger than some white dwarfs or ordinary stars, making them magnetically unremarkable despite their exotic interiors. All pulsars gradually slow down as magnetic fields and particle winds carry away rotational energy. This spin down is inexorable continuing as long as any magnetic field persists and the neutron star rotates. Young pulsars with strong fields and rapid rotation slow down quickly, perhaps losing half their rotational energy in just thousands of years. As rotation slows and fields weaken, the spin-down rate decreases. Eventually, pulsars slow to rotation periods of many seconds or even minutes. At this point, they may no longer produce detectable radio emission, either because the emission mechanism requires faster rotation or because the weakened magnetic field can no longer drive sufficient particle acceleration. These dead pulsars continue rotating but remain invisible to radio observations. They might still emit faint thermal X-rays from their surfaces or interact with their environments in subtle ways, but they no longer function as active pulsars. Millisecond pulsars, having been spun up to rapid rotation and possessing weak fields, slow down much more gradually. Some may continue as active pulsars for the age of the universe and beyond, their rotation rate stable enough to serve as cosmic clocks for billions of years. The neutron star population evolves over time, as new neutron stars form in supernovae, and old ones fade from observability. At any given time, the observable population includes neutron stars of various ages and properties. Young radio pulsars dominate searches with radio telescopes, appearing as strong sources with characteristic pulses. As they age and slow down, they become fainter and eventually drop below detection thresholds. The population of X-ray binaries changes as donor stars evolve and mass transfer rates vary. Some systems are transient, brightening for weeks or months before fading back to quiescence. Others maintain relatively steady X-ray emission for millions of years. Millisecond pulsars accumulate over time as more neutron stars undergo the recycling process through accretion. The millisecond pulsar population thus grows with galactic age, though it remains a small fraction of the total neutron star population. Magnetars likely represent a brief phase in neutron star evolution. Most neutron stars spend at most a few million years as active magnetars before their magnetic fields decay or reconfigure into more stable geometries. The magnetar population thus includes primarily young objects. On truly cosmic timescales, what becomes of neutron stars? They will continue cooling indefinitely, their surface temperatures approaching absolute zero as the universe expands and cools. Heat radiation will become negligible, with the neutron star becoming a dark cold sphere of degenerate matter. Rotation will slow to negligible rates if any energy loss mechanisms persist. Magnetic fields will decay, perhaps completely on timescales of tens of billions of years, leaving magnetically dead neutron stars. The neutron stars themselves should remain stable for extraordinary lengths of time. Unlike normal matter, which might decay if protons are unstable on timescales of 10 to the 34th power years or longer, neutron-rich matter may be more stable. If protons do decay, neutron stars might gradually evaporate as their small proton component undergoes decay. This would occur over timescales vastly exceeding the current age of the universe. Alternatively, neutron stars might persist essentially forever, or until quantum tunneling eventually converts their matter to black holes on timescales of 10 to the 65th power years. These timescales are so long that even the concept of eventually becomes almost meaningless. In the very far future of the universe, neutron stars may be among the last remaining structured objects floating through an ever-expanding, ever-colder cosmos. Neutron stars are not uniformly distributed throughout our galaxy. They cluster primarily in regions where massive star formation occurs, or has occurred recently. The galactic disk contains the majority of neutron stars, particularly within a few hundred light-years of the midplane. This reflects the distribution of massive stars that create neutron stars as their end products. The spiral arms show enhanced neutron star densities because star formation is more active in these regions. Young pulsars and supernova remnants cluster along the spiral arms, marking recent sites of massive star death. The galactic center region contains a higher density of neutron stars than typical disk locations. The enhanced star formation rate and the large population of stars in this region produce neutron stars at higher rates. Some neutron stars have been kicked to high velocities and now travel through the galactic halo above and below the disk. These high-latitude neutron stars are relatively rare but demonstrate the velocity kicks neutron stars can receive. Estimating the total neutron star population in our galaxy requires accounting for selection effects in our observations. We can only detect pulsars if their beams point toward Earth, and we can only see them if they're bright enough for our instruments. Current estimates suggest there may be around 100 million neutron stars in the Milky Way. Of these, perhaps 1 million are currently active as detectable radio pulsars, though we've only discovered a few thousand so far. The detection rate continues increasing as radio surveys become more sensitive and cover more of the sky. Each new telescope array finds previously undetected pulsars, both nearby objects that were too faint for earlier surveys and distant objects now accessible with improved sensitivity. Globular clusters, dense stellar systems orbiting in the galactic halo, contain disproportionately large numbers of millisecond pulsars relative to normal pulsars. This likely reflects the enhanced probability of binary interactions in these crowded environments, leading to more recycling through accretion. We can detect some neutron stars in nearby galaxies, primarily through X-ray emission from accreting systems, or through particularly bright pulsars visible in radio and other wavelengths. The Magellanic Clouds, small satellite galaxies of the Milky Way, host numerous detectable neutron stars. Observations of these systems test whether neutron star properties vary with galactic environment or metallicity. More distant galaxies occasionally show supernova explosions that we can observe. Some leave behind neutron stars, though detecting the individual neutron stars at such distances is generally impossible with current technology. Gravitational wave observations now allow us to detect neutron star mergers in galaxies hundreds of millions or billions of light-years away. While we cannot observe the individual neutron stars, before merger, the gravitational wave signal reveals their masses and provides statistical information about neutron stars in distant galaxies. The neutron star formation rate in galaxies varies with cosmic time. In the early universe, when metallicity was lower, massive star formation and neutron star creation may have occurred at different rates than today. As galaxies age and undergo chemical evolution, the proportion of massive stars capable of becoming neutron stars changes. Metallicity affects stellar evolution, potentially influencing whether a given massive star produces a neutron star or collapses directly to a black hole. Observations of element abundances in stars of different ages provide clues about how neutron star formation rates have changed. The accumulation of R-process elements reflects the integrated history of neutron star mergers over cosmic time. Comparing neutron star populations in galaxies at different redshifts might reveal evolution in neutron star properties. However, detecting individual neutron stars at cosmological distances remains beyond current capabilities except through gravitational wave observations. Neutron stars cannot exist at arbitrarily high masses. there is a maximum mass above which the neutron star matter cannot support itself against gravitational collapse. This critical mass depends on the equation of state of nuclear matter at high densities. Current estimates place the maximum mass somewhere between 2.0 and 2.5 solar masses. Though the exact value remains uncertain, different theoretical models predict different limits based on assumptions about nuclear forces and possible exotic matter phases. Observations of massive neutron stars help constrain this limit. The neutron star PSRJ 0348 plus 0432 has a measured mass of 2.01 solar masses. PSRJ 0740 plus 6620 may be even more massive at approximately 2.14 solar masses. These observations rule out equations of state that predict lower maximum masses. The maximum mass represents a fundamental boundary in nature. It marks the point where nuclear forces can no longer prevent gravitational collapse, where matter must transition from a neutron star to a black hole. Understanding this limit helps us understand nuclear physics at its extremes. It also affects predictions for what forms when neutron stars merge, or when matter accretes onto existing neutron stars in binary systems. When a neutron star exceeds the maximum mass, collapse to a black hole is inevitable. This might happen if a neutron star accretes enough mass from a companion star, or when two neutron stars merge and their combined mass exceeds the limit. The collapse occurs rapidly once it begins. The equation of state can no longer provide sufficient pressure to balance gravity. The matter falls inward, compressing to ever higher densities until an event horizon forms. From outside the event horizon, we would observe the neutron star's surface rapidly dimming and reddening as gravitational time dilation becomes extreme. Light emitted from the surface becomes increasingly redshifted and takes longer to escape. Eventually, all emission ceases as the horizon forms. The transition from neutron star to black hole represents one of the most extreme events possible. Matter that existed in an already exotic state undergoes compression to densities that may be infinite at the singularity, or that transition to unknown quantum gravitational states if singularities don't actually form. We have not definitively observed a neutron star collapsing to form a black hole, though we may have seen the aftermath in some neutron star merger events where the remnant appears to have collapsed rather than forming a stable massive neutron star. For many years, astronomers noticed a curious pattern. They observed neutron stars with masses up to about 2 solar masses and black holes with masses above about 5 solar masses. But very few objects appeared to exist in the range between 2 and 5 solar masses. This mass gap puzzled researchers. If neutron stars can exist up to some maximum mass, and if massive stars can collapse to form black holes, why weren't we seeing more compact objects in this intermediate range? Recent observations have begun filling in this gap. Some objects with masses between 2.5 and 5 solar masses have been detected, usually through gravitational wave observations of merger events. These discoveries suggest the gap may not be as empty as once thought. The apparent gap might be partly an observational effect. Objects in this mass range might be rare or difficult to detect through the methods commonly used to find neutron stars and black holes. They might also be genuinely rare due to how stellar evolution and supernova explosions produce remnants of different masses. Understanding the mass distribution of compact objects helps us understand stellar evolution, supernova physics, and the equation of state of ultra-dense matter. Each new discovery in this mass range provides clues about these fundamental questions. Time viennads av vienses slips vitra lielaxbar. Neutron star observations constrain theories of nuclear forces in ways laboratory experiments cannot. The extreme densities probe nuclear matter at conditions where many body effects dominate and perturbative calculations become difficult. The equation of state at high densities depends on the details of the strong nuclear force binding quarks within nucleons and binding nucleons into nuclei. Different theoretical models predict different stiffness for dense matter. By measuring neutron star masses and radii precisely, we can rule out equations of state that predict structures inconsistent with observations. A 2 solar mass neutron star requires a stiff enough equation of state to support that mass against collapse. Tidal deformability measurements from gravitational wave observations provide another constraint. The amount a neutron star stretches in its companion's tidal field depends on how compressible the matter is, directly related to the equation of state. Combining these constraints narrows the range of plausible equations of state. This in turn constrains nuclear physics theories and helps us understand the fundamental forces governing ultra-dense matter. Quantum chromodynamics, QCD, describes the strong force binding quarks into protons and neutrons. At low densities, quarks are permanently confined within hadrons. At very high densities or temperatures, theory predicts a transition to a quark-gluon plasma, where quarks move freely. Neutron star cores might reach densities where this transition occurs. If so, the cores could contain quark matter, rather than, or in addition, to nuclear matter. The transition might be a sharp phase boundary, or a smooth crossover. Studying how neutron stars respond to tidal forces, how they cool, and how their oscillation modes behave might reveal signatures of quark matter if it exists. Different theoretical models of the QCD phase diagram make distinct predictions for neutron star properties. Lattice QCD, calculations performed using supercomputers to solve QCD equations on discrete spacetime grids, predict matter properties at high densities. Comparing these predictions to neutron star observations tests our understanding of QCD in regimes inaccessible to collider experiments. Neutron stars also constrain speculative physics beyond the standard model. Hypothetical particles predicted by various extensions to our current theories would affect neutron star properties if they exist. Axions, if they exist and have the right mass range, would be produced in neutron star cores through nuclear reactions and decays. They would escape freely, cooling the neutron star faster than neutrinos alone. Comparing observed cooling rates to theoretical predictions constrains axion properties. Dark matter particles might accumulate in neutron stars over millions of years if they interact with normal matter even very weakly. The accumulated dark matter could affect the maximum mass, alter cooling rates, or eventually trigger collapse to black holes if enough accumulates. Extra spatial dimensions, predicted by some approaches to unifying gravity with quantum mechanics, might affect gravitational dynamics around neutron stars. Deviations from general relativity's predictions in binary pulsar timing or gravitational wave observations could reveal these extra dimensions. Violations of Lorentz invariance, the principle that physics is the same in all inertial reference frames, might manifest differently in neutron star environments than in solar system tests. Pulsar timing arrays search for patterns in timing residuals that might indicate Lorentz violation. So far, neutron star observations have found no evidence for exotic physics beyond the standard model and general relativity. The increasingly precise measurements set ever tighter constraints on hypothetical new particles and forces. Neutron stars also connect to cosmology through their role in element creation and their use as tools for measuring cosmic distances. the R-process elements created in neutron star mergers have been building up in galaxies throughout cosmic time. By measuring elemental abundances in stars of different ages, we trace how element production rates have varied as the universe evolved and galaxies formed. Old stars with low, heavy element abundances formed when the galaxy was young and few neutron star mergers had occurred. Younger stars show higher heavy element abundances, reflecting billions of years of continued element production. Gravitational wave observations of neutron star mergers provide a new way to measure the universe's expansion rate. By comparing the gravitational wave amplitude, which depends on distance, to the redshift of the host galaxy, which depends on expansion rate, we can determine the Hubble constant independently of other methods. This approach avoids some systematic uncertainties affecting traditional distance ladder measurements. As more neutron star mergers are detected, statistical uncertainties will decrease, potentially helping resolve current tensions between different Hubble constant measurements. Current gravitational wave detectors like LIGO and Virgo have opened new windows into neutron star physics. Future detectors will expand these capabilities substantially. Third-generation ground-based detectors like Einstein Telescope and Cosmic Explorer will have sensitivity roughly 10 times better than current instruments. They'll detect neutron star mergers from much greater distances, potentially seeing hundreds or thousands of events per year rather than a handful. This large sample will enable statistical studies of neutron star properties, will better constrain the equation of state by measuring mass and tidal deformability for many systems. We'll learn about the neutron star mass distribution and binary evolution through population studies. Space-based detectors like LISA will observe at lower frequencies, detecting earlier stages of binary evolution. For neutron star binaries, this means observing systems years or decades before they merge, providing advance warning for electromagnetic telescopes. Next-generation radio telescope arrays like the Square Kilometre Array will revolutionize pulsar astronomy. With sensitivity far exceeding current instruments, SKA will detect many more pulsars, including fainter and more distant objects. The improved timing precision will enable better tests of general relativity and searches for gravitational waves using pulsar timing arrays. We'll measure orbital parameters with unprecedented accuracy and detect subtler effects in complex binary systems. SKA will also discover more millisecond pulsars in globular clusters and more rare systems like double pulsars, where both neutron stars are visible from Earth. Each discovery expands our ability to test physics under extreme conditions. Future X-ray telescopes will combine larger collecting areas with better spectral resolution and improved timing capabilities. Planned missions will provide order of magnitude improvements over current observatories. These capabilities will enable detailed studies of neutron star atmospheres, measuring gravitational redshift and magnetic field strengths through spectral line analysis. They'll detect fainter thermal emission from old neutron stars, extending cooling curve measurements to longer timescales. Improved timing will resolve rapid oscillations during X-ray bursts and Magnetar outbursts, probing neutron star interiors through asteroseismology. Different oscillation modes sample different regions of the star and depend on the equation of state in distinct ways. Future neutron star observations will increasingly combine data from gravitational wave detectors, electromagnetic telescopes across all wavelengths, and potentially neutrino detectors. When gravitational waves from a merger are detected, rapid alerts will allow electromagnetic telescopes to observe the kilonova from the earliest moments. Early observations catch the hottest phases, and provide crucial data for modeling the R process, nucleosynthesis. Coordinated campaigns will track how kilonovae evolve, measuring light curves and spectra across many wavelengths simultaneously. This reveals temperature evolution, ejecta expansion, and the development of spectral features from different heavy elements. For nearby events, neutrino detectors might catch the neutrino burst from a supernova, creating a neutron star. The neutrino signal carries information about the collapse process and core formation that electromagnetic observations cannot reveal. Despite decades of study, many fundamental questions about neutron stars remain unanswered. What is the equation of state of nuclear matter at densities above nuclear saturation density? Do exotic particles like hyperons or quarks exist in neutron star cores? How do superfluidity and superconductivity behave at these extreme densities and temperatures? What determines whether a massive star produces a neutron star or collapses directly to a black hole? What sets the initial spin and magnetic field of newly formed neutron stars? Why do some become magnetars while most have weaker fields? How do magnetic fields evolve over millions of years? What triggers Magnetar outbursts? Why do some neutron stars show mode changes or nulling, while others pulse steadily for decades? What mechanisms accelerate particles to extreme energies in pulsar magnetospheres? How does the plasma structure support coherent radio emission? What determines the geometry and intensity of emission beams? Future observations will address these questions, but will likely raise new ones as we probe deeper into extreme physics regimes. Neutron stars connect stellar death to cosmic chemical evolution through the R process elements they produce. This represents one of the most direct links between stellar evolution and the development of chemical complexity in the universe. Without neutron star mergers, the universe would have drastically different element abundances. Heavy elements crucial for certain technologies and biological processes would be rare or absent. Rocky planets might form with different compositions, potentially affecting their geological evolution and habitability. This chain from stellar death to element creation to planet formation to potential life represents a fundamental cycle in cosmic evolution. Neutron stars play an essential role as the sites where the heaviest elements are forged. Neutron stars serve as natural laboratories where we can study physics in regimes inaccessible to terrestrial experiments. The densities, magnetic field strengths, and gravitational fields reach values we cannot replicate on Earth even in principle. Observations of neutron stars thus provide crucial tests of theoretical predictions about nuclear matter, magnetic field physics, and gravity under extreme conditions. They constrain theoretical models and sometimes reveal unexpected phenomena that drive new theoretical developments. This interplay between observation and theory advances our understanding of fundamental physics. Each new measurement either confirms existing theories or points toward needed modifications. The most stable millisecond pulsars serve as precise clocks visible across interstellar distances. Their pulse arrival times can be measured with microsecond precision, allowing long-term monitoring for subtle effects. Pulsar timing arrays use collections of millisecond pulsars as a galaxy-spanning gravitational wave detector. Gravitational waves passing through our region of space create correlated timing variations across multiple pulsars that can be detected through careful analysis. This technique is sensitive to gravitational waves with periods of years, far longer than ground-based detectors can access. It may detect gravitational wave background from supermassive black hole binaries in galaxy centers throughout the universe. Neutron stars represent one endpoint of stellar evolution for massive stars. Their properties reflect the details of the progenitor stars and the supernova explosions that created them. by studying neutron star masses, rotation rates, and magnetic fields, we learn about massive star evolution, core collapse dynamics, and explosion asymmetries. Each neutron star carries information about its formation encoded in its current properties. Binary neutron stars reveal how massive binary stars evolve, how they interact through mass transfer and common envelope phases, and how these processes affect the final products. The diversity of binary configurations reflects the variety of evolutionary pathways. Neutron stars also invite philosophical reflection on the nature of matter and the universe's capacity for creating extreme conditions. These objects demonstrate that matter can exist in states wildly different from everyday experience, yet still be governed by the same fundamental laws of physics. The exotic matter in neutron star cores follows from the same quantum mechanics and nuclear forces that govern atoms in our bodies. The precision of neutron star observations tests our theories to extraordinary accuracy, confirming that the mathematical laws we discover through terrestrial experiments apply throughout the universe, even under the most extreme conditions. Neutron stars connect the smallest scales of quarks and nuclear forces to the largest scales of galactic structure and cosmic evolution. They exemplify how physics operates across an enormous range of scales, with the same fundamental principles applying from subatomic to cosmic phenomena. Neutron stars represent some of the most extreme objects in the universe, yet they remain governed by physical laws we can understand and test. Their densities exceed nuclear densities. Their magnetic fields dwarf anything achievable in laboratories. Their gravitational fields warp spacetime significantly. Yet all these phenomena follow from the same quantum mechanics, nuclear physics, and general relativity that describe less extreme systems. This is remarkable. The laws of physics discovered through experiments in terrestrial laboratories apply faithfully to conditions orders of magnitude more extreme. The equations remain valid. The predictions hold. The universe exhibits a deep unity across vastly different regimes. Neutron stars connect physics at the smallest scales to phenomena at astronomical scales. Quarks and nuclear forces determine the equation of state, which in turn determines whether a neutron star can support a given mass or must collapse to a black hole. Quantum mechanics governs superfluidity in the interior, which affects how glitches propagate and how the neutron star cools. General relativity describes how space-time curves around these objects and how binary systems spiral together. These connections mean that observations of astronomical objects light years away can test theories about subatomic particles and fundamental forces. The cosmos becomes a laboratory, extending our experimental reach far beyond what we can achieve on Earth. Neutron stars participate in cosmic recycling, the process by which matter transforms from one form to another over cosmic time. The heavy elements created in neutron star mergers eventually become incorporated into new generations of stars and planets. This recycling operates on timescales of hundreds of millions to billions of years. Material moves from stars to interstellar space through supernovae and mergers, then back into stars through gravitational collapse of gas clouds, then into planets through accretion during planet formation. We are products of this recycling. The atoms in our bodies were created in stars, dispersed through space by stellar explosions, and eventually incorporated into Earth during its formation. Some of the heaviest elements came specifically from neutron star mergers billions of years ago. Neutron star observations will continue revealing new physics as our instruments improve. Next-generation gravitational wave detectors will observe thousands of mergers, constraining the equation of state to unprecedented precision. Advanced radio telescopes will find more exotic binary systems and enable more precise tests of general relativity. Improved X-ray observatories will measure neutron star radii accurately through detailed spectroscopic and timing analysis. Multi-messenger observations combining gravitational waves, electromagnetic radiation, and potentially neutrinos will provide comprehensive views of neutron star physics. Each new capability opens possibilities for discoveries we haven't yet imagined. Why study neutron stars? Beyond the immediate scientific discoveries, understanding these objects enriches our comprehension of the universe we inhabit. They demonstrate the range of conditions that can exist in nature. They test our theories in ways terrestrial experiments cannot. They reveal connections between apparently separate areas of physics. Perhaps most importantly, they inspire wonder at the universe's capacity for creating phenomena more remarkable than imagination could devise. Neutron stars exist. They are real objects that formed from stellar death, creating matter in states we can barely describe, forging the heaviest elements, and serving as laboratories for extreme physics. In the quiet of night, radio telescopes detect pulses from neutron stars spinning hundreds of times per second. X-ray satellites observe sudden bursts from magnetars undergoing crustal fractures. Gravitational wave detectors measure space-time ripples from merging neutron stars billions of light-years away. These observations reveal a universe far stranger and more remarkable than everyday experience suggests. Yet it's all comprehensible through physics, mathematics, and careful observation. Neutron stars, despite their exotic nature, follow the same laws that govern falling objects and orbiting planets. The universe exhibits a profound unity. The same principles operate from the quantum to the cosmic scale. As we continue studying these objects, we simultaneously test our theories, expand our knowledge, and develop a deeper appreciation for the cosmos in which we find ourselves. Each observation adds to our understanding. Each discovery raises new questions. The journey continues. Neutron stars will keep revealing their secrets as our instruments improve and our theories develop. We've learned much already, but much remains to discover. Neutron stars formed from the death of massive stars. They compressed matter to densities beyond nuclear densities. They generate magnetic fields trillions of times stronger than Earth's. They spin hundreds of times per second. They merge in collisions that forge gold and platinum. All of this follows from physics we can understand. The equations work. The observations match predictions. The universe makes sense. This consistency across such extreme conditions suggests something profound about the nature of physical law. The rules governing atoms govern neutron stars. Quantum mechanics applies at cosmic scales. General relativity accurately describes strong gravitational fields. We inhabit a comprehensible universe. The same curiosity that drives us to understand everyday phenomena enables us to comprehend neutron stars light-years away. The same mathematics describes both. This is reason enough to study these objects, not just for practical applications or technological spin-offs, but for the pure satisfaction of understanding one of the universe's most remarkable phenomena. Neutron stars exist. They are real. And through observation, theory, and careful analysis, we can understand them. That understanding connects us to the cosmos in ways both intellectual and profound. It reveals the universe as a place where extreme conditions create exotic phenomena, yet fundamental laws remain constant. As you rest, perhaps reflect on this. The atoms in your body came from stars. Some of the heaviest elements came from neutron star collisions. You are literally made of stardust, forged in cosmic fires and scattered through space. Neutron stars aren't just astronomical objects to study. They're part of the vast cosmic story that includes us. Understanding them helps us understand our place in this remarkable universe. Rest well. The neutron stars continue their cosmic dance, spinning through space, cooling over eons, occasionally colliding to forge new elements. They've been doing this for billions of years. They'll continue for billions more. And we, for this brief moment in cosmic time, have the privilege of observing them, measuring them, and beginning to understand them. The universe is vast. It's ancient. It's filled with phenomena more extreme than imagination alone could conjure. Yet through patient observation and careful thought, we can comprehend it.